In 1959, a man vanished on a boat trip down the Danube. There was a suspect. There was no body, no witness, and no confession, and without a body, Austrian prosecutors had almost nothing. What they had was a pair of boots with mud on them. A scientist at the University of Vienna washed the mud off, put it under a microscope, and found pollen. Spruce, willow, alder, ordinary enough for a river valley, and among it, grains of hickory pollen that were roughly 20 million years old. Hickory does not grow in Austria and has not for millions of years. But the pollen was there, preserved in a fossil deposit that outcrops in exactly one small stretch of the Danube Valley, about 20 kilometers north of Vienna. The scientist could therefore say something extraordinarily specific: this mud came from there, not from the region. From a particular few square kilometers, identifiable because of a geological accident that happened before there were people to walk on it. The suspect was shown the finding, he confessed, and he led the police to the grave, which was in exactly the area the pollen indicated. This is the story of how the reproductive dust of plants became forensic evidence, why it is one of the most location-specific traces a person can carry, and why, despite all that, it is still barely used. Start with what pollen actually is, because the physical properties are the entire basis of the technique. Pollen is how seed plants reproduce. Each grain carries the male genetic material to a receptive female structure by wind, by water, or on an insect. Plants produce it in quantities that are difficult to comprehend. A single birch catkin can release several million grains. A hectare of pine forest can put tens of kilograms of pollen into the air in a season. In spring, the air over much of the temperate world contains thousands of grains per cubic meter. That is the first property that matters. It is everywhere in enormous numbers and nobody can avoid it. The second property is durability, and it is the remarkable one. The outer wall of a pollen grain is made of a substance called sporopollenin. It is one of the most chemically resistant organic materials known. It resists acid, alkali, oxidation, heat, and microbial attack. It survives conditions that destroy virtually all other organic matter. Palynologists routinely extract intact, identifiable pollen from sediments tens of millions of years old. The processing itself involves treatment with hydrofluoric acid, which dissolves rock, and the pollen comes through it unharmed. So a grain of pollen that lands on a coat in April is still there, still identifiable months or years later, unless it is physically removed. The third property is identifiability. Pollen grains differ between plant species in shape, size, wall structure, and the arrangement of the apertures through which the pollen tube emerges. Under a microscope, a trained analyst can identify most grains to genus and many to species. That is what makes the technique possible: ubiquitous, indestructible, and identifiable. Now the crucial step, which is why this is evidence rather than trivia. A single pollen grain tells you almost nothing. Birch pollen is on everything in a birch region. What carries information is the assemblage, the full set of species present, and crucially their relative proportions. A sample containing 60% pine, 15% birch, 8% grasses, traces of heather, and a scattering of unusual ornamentals describes a specific plant community in a specific place. That combination is called a pollen spectrum, and its usefulness comes from the fact that plant communities vary at surprisingly fine scales. Two woodlands a kilometre apart can produce measurably different spectra, because the mix of species differs, and because gardens, hedgerows, and planted specimens introduce local peculiarities. An ornamental tree in one garden and not another is a marker. So the question a palynologist can answer is not, what plants are near this? It is, how well does this sample match that place, and how many other places would it also match? Now back to the 1959 case, because the details of that first conviction show the method being invented under pressure. A man had disappeared during a boat trip on the Danube near Vienna. Police suspected a particular individual but had no body, and in a case without a body, the practical difficulty is not only proving a death, but proving that the suspect was ever at a relevant location. They searched his home and found a pair of muddy boots. Mud is common, muddy boots prove nothing. They sent the mud to Wilhelm Klaus, a palynologist at the University of Vienna who was working on the geology of the Danube basin. He was not a forensic scientist, he was a specialist in ancient pollen who happened to know the local deposits extremely well. He found the expected modern pollen, the trees and grasses of the valley, and then he found the hickory. Fossil pollen occurs in soil where ancient sediments outcrop at the surface and erode. The Miocene deposits containing that hickory pollen are exposed in a limited area of the valley. Anywhere else, the modern pollen would be present and the fossil grains would not. That is what made the identification so tight. The modern spectrum said Danube Valley. The fossil component said, and specifically here, where these particular ancient beds reach the surface. Klaus was able to indicate an area of a few square kilometers. The confession is the part that is usually reported, and it deserves a note of caution. He was confronted with the finding and confessed, and the body was recovered where the pollen suggested. So the evidence was never tested by cross-examination in the way it would have been at a contested trial. That matters for how much weight the case can bear as a precedent. It demonstrated that the technique could produce a usable geographic conclusion. It did not establish how the conclusion would survive an aggressive defense expert, because there wasn't one. Now how the technique has been used since, because there is a pattern to which cases it suits. Palynology answers a specific class of question: was this object or this person in that place? It is not an identification technique, it says nothing about who someone is. It cannot establish a cause of death or a time of death, though it can sometimes constrain a season. It is most useful where an object has been moved, and the question is where it has been. In New Zealand, a case involving stolen items was resolved when pollen on the recovered goods matched a specific property where the theft was denied. In several British investigations, soil and pollen from a suspect's vehicle have been compared with deposition sites, the tire arches and footwells of a car being particularly good traps for material picked up on rough ground. In a well-documented British case, the location of a clandestine grave was narrowed by analysing pollen on a spade recovered from a suspect, which carried a spectrum matching a particular woodland rather than the surrounding farmland. And in a use that has nothing to do with individual crimes, pollen analysis has been applied to trace the geographic origin of drug shipments, of counterfeit goods, and of smuggled artifacts, because a crate that has sat in a warehouse in one country carries the pollen of that country's flora. There is also a body of work on honey. Honey carries the pollen of the flowers the bees visited, so a jar labeled as coming from one country can be tested against the plant community of that country. Fraudulently relabeled honey is detectable this way, and the technique is used commercially. Now the practical difficulties, because they explain the technique's obscurity better than any conspiracy would. The first is that it requires a specialist, and there are very few of them. Palynology is a small academic discipline, mostly serving geology, archaeology, and climate reconstruction. Forensic palynologists, people who both know pollen and understand the evidentiary requirements of a court, number in the dozens worldwide, and for much of the technique's history in the handful. New Zealand has been unusually active, largely because of the sustained work of a small number of researchers. Britain has developed capability. Much of the world has essentially none. An investigator cannot use a technique for which no local practitioner exists, and will not think of a technique they have never seen used. The second difficulty is that it requires reference data. To say a sample matches a place, you need to know what that place produces, which means collecting control samples from the site and from comparison sites, and understanding seasonal variation, because the spectrum in April differs from the spectrum in September. That is real fieldwork done after the fact, and it takes time. A technique that requires several weeks of comparative sampling does not fit comfortably into an urgent investigation. The third is contamination and transfer, which is the serious scientific objection. Pollen moves, it is designed to move. Grains travel on the wind for kilometers and in some cases hundreds. So the presence of a species in a sample does not prove proximity to that species. This is why the assemblage matters more than any single component, and why proportions matter more than presence. Long-distance transport contributes a low, diffuse background of common wind-pollinated species. A high proportion of an insect-pollinated species, which does not travel far, is much stronger evidence of local contact. A competent analyst works with those distinctions constantly. An incompetent one, or one under pressure to help, could produce something that sounds compelling and means very little. The fourth is that it can be transferred innocently between people and objects. Shaking hands, sharing a car, or handling the same coat can move pollen. That is not a fatal objection. The same is true of fibers and of DNA, but it means the finding has to be framed as contact with an environment rather than presence at a scene. Which brings us to the standard this discipline has to meet, and it is the standard that several other forensic techniques failed. Bite mark comparison was admitted for decades and has since been found to lack scientific foundation. Microscopic hair comparison produced testimony that the FBI itself later reviewed and found overstated in the great majority of cases examined. Both were pattern-matching disciplines created largely for courtrooms. Palynology is in a materially different position, and it is worth being precise about why. It is a real scientific discipline with an existence independent of the legal system. Palynologists reconstruct ancient climates, date sediments, and advise oil exploration on the age of rock formations. That work has customers who lose money when the answer is wrong, and it has been doing it since long before anyone thought of using it on a pair of boots. The identification of pollen grains to genus is not a subjective impression of similarity. It is based on described morphological features, with reference collections and published keys, and it can be checked by another analyst working blind. And the interpretive step, this assemblage resembles that location, is quantifiable in principle. You can count grains, calculate proportions, and state how many comparison sites produce a similar spectrum. That is the difference between a technique that can be validated and one that cannot. It does not mean palynological evidence is always well presented, but it means the underlying discipline is capable of supporting the claims made in its name, which is more than could be said for bite marks. There is, though, a genuine weakness that should be stated plainly. There is no large database of pollen spectra against which a match probability can be calculated. In DNA analysis, a match can be expressed as a frequency in a reference population. In palynology, the analyst can say the spectra are consistent and that a match is unlikely to be coincidental, but the unlikely is a judgment informed by experience rather than a number derived from a dataset. That is exactly the kind of gap where forensic disciplines have historically gone wrong, an expert's confidence substituting for a measured error rate. The honest position is that the technique is sound and the quantification is immature, and that the second of those should constrain how strongly conclusions are phrased. Now, why so little used, given all that? Part of it is the specialist shortage already described, part is the reference data problem, but a substantial part is simply that investigators do not know it exists. Forensic technique adoption is driven by what practitioners have seen work. Fingerprints and DNA are known to every officer. Pollen is known to almost none, and there is no mechanism by which an investigator in a jurisdiction with no palynologist would ever encounter it. That produces a self-sustaining absence, not used, therefore not known, therefore not used. There is a further factor, which is that pollen evidence usually needs to be collected early and specifically. It is not something that can be retrieved later from an evidence bag that was never sealed with that purpose in mind. Clothing packed in plastic and stored damp will grow mold, which does not destroy the pollen but complicates the analysis. Items washed, brushed down, or handled without gloves lose or gain material. Soil scraped off a boot and discarded as dirt is gone. So the technique's usability is decided at the scene, hours before anybody has thought about pollen, and by people who have no reason to think about it. That is a solvable problem, and it is solved by training rather than by technology. It has been solved in New Zealand and partially in Britain. It has not been solved in most places. There is one more consideration that makes this technique more interesting now than it was. Modern analysis can extract far more from a small sample than was possible in 1959. Klaus was working with a microscope and his own knowledge of local deposits. A modern analyst has automated counting assisted by image recognition, DNA barcoding of plant material in a sample, and geographic information systems that can model expected vegetation across a landscape. DNA metabarcoding in particular changes the arithmetic. Instead of identifying grains visually one at a time, it is possible to sequence plant DNA present in a soil or dust sample and produce a list of species, including ones whose pollen is hard to distinguish morphologically. That does not replace classical palynology. The two answer slightly different questions and have different failure modes. But it substantially raises the resolution available, and it reduces the dependence on a small number of highly trained eyes. Which means the practical objection that there are too few people who can do it is weakening. It is worth walking through what an analysis actually involves, because the labor is invisible in every account of these cases, and it explains a great deal about the technique's limits. Start with the sample. A palynologist working on a pair of boots does not analyze the boot. They recover the adhering material, soil, dust, plant fragments, usually by careful scraping over clean paper, keeping different areas separate. The sole is treated differently from the upper because they pick up material at different times and from different surfaces. Then the sample is processed to isolate the pollen from everything else in it, and the chemistry involved is genuinely aggressive. Carbonates are dissolved with hydrochloric acid. Silicates, sand and clay, which make up most of the sample by weight, are dissolved with hydrofluoric acid. Organic material other than sporopollenin is broken down by acetylosis, a mixture of acetic anhydride and sulfuric acid applied hot. At the end of that, what remains is essentially pollen and spores, because almost nothing else in nature survives the process. That resistance is exactly why the technique works and why the processing can be so brutal. The residue is mounted on slides and counted. A standard count is several hundred grains, identified individually under high magnification and recorded by type. Several hundred identifications, one at a time by eye. That is where the specialist requirement really lies. Identification depends on recognizing fine morphological features, the number and arrangement of apertures, the sculpturing of the outer wall, the size and shape, across hundreds of possible taxa, with reference collections and published keys as support. An experienced analyst can do it reliably. Somebody who has read about it cannot, and the failure mode is not a blank result but a confident wrong one. Then the comparison, which is the interpretive heart of it. The question sample spectrum is compared with control samples collected from candidate locations and with a general picture of the regional flora. The analyst is asking two things. Does the question sample resemble this place, and how distinctive would that resemblance be? The second question is the one that carries the weight. A spectrum dominated by pine and birch in a pine and birch region says almost nothing. A spectrum containing a particular ornamental species, a locally unusual weed, and a fossil component from an outcropping deposit says a great deal, because the number of places that would produce that combination is small. So the strength of the conclusion depends entirely on how unusual the assemblage is, and a good analyst says so explicitly rather than presenting all matches as equivalent. Now the seasonality question, because it is a genuine complication and also an opportunity. Pollen production is seasonal and the calendar is species-specific. Alder and hazel release in late winter, birch in spring, grasses through early summer, many herbs later still. So the pollen rain at a given place changes substantially through the year. That complicates matching, because a control sample collected in October will not resemble a question sample deposited in May, even from the same spot. But it also means that a spectrum can constrain a time of year. If a sample contains abundant fresh grass pollen and no autumn types, that points to a window. In a case where the date of an event is disputed, that is potentially valuable, and it is a question no other trace evidence can answer in the same way. There is a limit to it. Pollen persists in soil for years, so a soil sample contains an accumulation of many seasons, not a snapshot. The seasonal signal is strongest in material captured from the air or from a surface shortly after deposition, clothing, hair, a vehicle's air filter, rather than from soil. Which points at where the technique is most powerful, and it is not soil at all. An air filter is close to an ideal palynological sample. A vehicle draws air through it continuously while driving, and pollen accumulates in it in rough proportion to the environments the vehicle has passed through, layered over time. Analyzing a cabin filter can therefore indicate not only where a vehicle has been but something about the sequence, because the accumulation is stratified. That is considerably more informative than a scraping of mud, and it is a sample that almost nobody thinks to seize. The same logic applies to clothing that has not been washed, to the interiors of bags, and to hair. Now, a broader point about why this class of evidence is undervalued in general. There is a hierarchy in how investigators think about forensic traces, and it is largely determined by how directly the trace points at a person. DNA identifies an individual, fingerprints identify an individual, those sit at the top. Pollen identifies a place, so does soil, so does diatom analysis in drowning cases, so does isotope analysis of hair for recent geographic history. Place-based evidence is systematically underused because it does not answer the question investigators feel they are asking. But in a great many cases, the identity of the suspect is not in doubt at all. What is disputed is whether they were somewhere, or where something happened, or where an object came from. For that class of question, place-based evidence is not a poor substitute for DNA. It is the correct tool, and DNA cannot answer it. The 1959 case is the plain illustration. The police knew who they suspected. They did not know where the body was, and they could not place the suspect at any relevant location. Identity evidence would have added nothing. Location evidence solved it. There is a further category worth mentioning, because it is where the technique has quietly become routine. Customs and trade enforcement use pollen and plant DNA to check the claimed origin of goods. Timber, honey, herbal products, and agricultural produce all carry a botanical signature of where they were grown or processed. That is a substantial commercial application, running continuously, and it has a useful property. It generates a stream of real-world tests where being wrong has consequences. A laboratory that misidentifies the origin of a timber shipment finds out, which is precisely the quality control mechanism that pattern comparison disciplines invented for courtrooms have always lacked. Palynology has an independent customer who checks the work, and that is worth more to its reliability than any accreditation scheme. There is a final observation, and it is the one worth taking away. The reason pollen works is not that it is exotic, it is that it is unavoidable. A person planning a crime can wear gloves, avoid touching surfaces, dispose of clothing, clean a vehicle, and avoid cameras. Every one of those is a deliberate countermeasure against a known form of evidence. Nobody takes countermeasures against pollen because nobody thinks about it. It is invisible, it is on everything, it cannot be felt or seen or brushed away with any confidence, and it records where you have been in a form that survives almost anything you could do to it. The 1959 case turned on a substance that had been sitting in the ground for 20 million years, waiting, in a specific few square kilometers of Austria, for somebody to walk through it. That is the useful thought. The most informative evidence at a scene is rarely the thing an offender was careful about. It is the thing they did not know was there. There is one more case worth setting out, because it shows the technique doing something the 1959 case did not, surviving a contested trial. In Britain in the early 2000s, a body was found on farmland and a suspect denied ever having been at the deposition site. His vehicle had been cleaned. There were no witnesses and no useful camera coverage. Material was recovered from the vehicle's footwells and pedals, and from a pair of boots. The palynological analysis found a spectrum that included several species characteristic of the specific field margin where the body was found, including an insect-pollinated species that does not disperse far on the wind, which is the strongest kind of indicator because its presence implies close physical contact with the plant rather than atmospheric drift. The defense made the correct arguments, that pollen travels, that the species were present across the wider area, and that transfer could have occurred innocently. The analyst's response is the model for how this evidence should be given. She did not claim the sample proved presence. She stated the proportions, distinguished wind-borne background from locally deposited material, described how many comparison sites had been sampled and how they differed, and gave a conclusion framed as strength of support rather than as certainty. That is the difference between palynological evidence that holds up and the kind that should not be admitted. The claim was about the material, stated with its limits attached, and the inference to guilt was left to the jury. Compare that with the bite mark testimony that has since been overturned, in which examiners routinely told juries that a mark matched a defendant to the exclusion of all others, a claim with no data behind it and no way of being wrong. The technique is not what makes evidence safe. The sentence the expert is willing to say is what makes it safe. Now a word about what a defense should ask, because it is the same list a good analyst applies to themselves. How many comparison sites were sampled, and how different were they? A match to one site means little if no alternatives were tested. What proportion of the assemblage is wind-pollinated, and what proportion insect-pollinated? The second is the part that indicates contact. When were the control samples collected relative to the event, and does the seasonality match? What is the chain of custody, and was the item packaged in a way that prevented contamination? Paper, not plastic, sealed at the scene, not later. And crucially, could the analyst have been influenced by knowing what conclusion was wanted? Was the analysis done blind to the police theory, or after being told where the sample was supposed to have come from? That last question is the one that has undone more forensic evidence than any other in every discipline. It is not about honesty. It is about the ordinary human tendency to find what you are looking for in ambiguous material, and the only defense against it is procedural. Which is a fitting note on which to end, because it is the same lesson every one of these techniques teaches. The science is usually fine, pollen really is everywhere, really is indestructible, and really does record location with remarkable precision. What determines whether that produces a safe conviction or an unsafe one is entirely a matter of how the work is organized, whether the analyst knew the answer in advance, whether alternatives were tested, and whether the conclusion was stated with its limits or without them. 20 million years of geological patience put that hickory pollen in the Danube Valley. What made it evidence was a man who knew exactly which few square kilometers it could have come from, and who said only that. There is a postscript worth adding about the man who started it, because his position was unusual, and it is part of why the technique took so long to spread. Wilhelm Klaus was not building a forensic discipline. He was a paleobotanist working on the stratigraphy of the Vienna Basin, using pollen to date and correlate rock formations, which is what palynologists mostly do. The police approached him because he happened to be the person in Vienna who knew what was in that soil. So the founding case of forensic palynology was solved by somebody who had no interest in forensic palynology, using knowledge assembled for an entirely unrelated purpose. That is a recurring shape in the history of forensic science, and it is worth naming. Arthur Kohler and the Lindbergh ladder is the same story, a wood technologist at a federal timber laboratory, applying an existing industrial science to an object nobody had thought of as evidence. In both cases, the technique held up precisely because it was not invented for the courtroom. And in both cases, the discipline stayed small afterwards because the founder went back to their actual job. Compare that with the techniques that expanded fast to meet legal demand and which have since produced waves of overturned convictions. The correlation is not subtle. There is one more practical consequence of that history. Because these techniques come from outside, the people who can perform them are usually employed by universities, museums, and industry rather than by police laboratories. They are not on any forensic provider's staff list, and they are not in any procurement framework. An investigator who wanted a pollen analysis in most jurisdictions would not know who to telephone, not because nobody can do it, but because the people who can are filed under geology. That is a genuinely solvable problem, and solving it costs almost nothing compared with developing a new technique. It requires a list. Which is perhaps the most useful thing to take from all of this. The barrier to using pollen evidence is not scientific, and it is not financial. It is that the relevant expertise sits in a different building, under a different job title, and no mechanism exists to connect it to the people who need it. The 1959 case happened because a Viennese detective knew a botanist. That is still, in a great many places, the only mechanism there is. There is a last strand worth following, about what pollen can do that nothing else can, establish that a body has been moved. Consider a case where remains are found in one location, and the question is whether the death occurred there or elsewhere. That distinction matters enormously. It separates a deposition site from a murder scene, and it changes what investigators should be looking for and where. Ordinary evidence struggles with it. The absence of blood at a scene is suggestive but weak. Insect evidence can indicate how long remains have been in a place, but not necessarily where they were before. Pollen answers it directly, because clothing and hair carry the assemblage of every environment they have passed through layered. If a body is found in open farmland, but the clothing carries a heavy woodland spectrum, abundant tree pollen, shade-tolerant herbs, species that do not grow in the field it was found in, that indicates prior contact with woodland. It does not say which woodland, unless there is something distinctive, but it establishes movement and it points the search. The same logic applies to vehicles. If a car's footwell carries a spectrum from a habitat the driver claims never to have visited, that is a statement about the vehicle's history that the driver's account has to accommodate. That capability, reconstructing an object's path through environments, has no real equivalent among the standard forensic traces, and it is the strongest argument for the technique's wider use. There is also its role in cases that are not crimes at all. Palynology has been used to establish the season of death in archaeological remains, to determine whether a body recovered from water entered it upstream or downstream, and in disaster victim identification, to indicate where remains had been before they were recovered. And it has been used the other way round to exclude. A suspect's clothing that carries no trace of a distinctive site's assemblage, when a control shows that anyone present would have picked it up abundantly, is evidence of absence rather than presence. Exclusion is the underrated half of forensic science, and it is worth saying explicitly. A technique that can only ever incriminate is a technique that is being used wrongly. The value of pollen is that its absence is informative too, provided somebody has established what a person present would have carried away. That requires the control sampling described earlier, which is the part everybody wants to skip, and skipping it is what turns a genuine science into an assertion. So the honest summary of this technique is neither the enthusiastic version nor the dismissive one. It is a real science, with an existence independent of the courts, capable of remarkably specific geographic conclusions, applied by a very small number of people, requiring fieldwork that investigations rarely budget for, and dependent for its safety on procedural discipline that is easy to describe and easy to omit. Which is a description that fits almost every forensic technique worth having. And the reason to know about it, even if you will never stand in a laboratory, is the habit of mind it encourages. An offender thinks about what can be seen: cameras, witnesses, fingerprints, blood, the traces that have a name and a reputation. Every countermeasure is aimed at those. The traces that solve cases are frequently the ones with no reputation at all. The insects that arrived on their own schedule, the grain of a floorboard, the pollen that had been sitting in the ground since the Miocene. Not because they are cleverer, because nobody defends against a thing they have never heard of.